All right, good evening, everybody, and thanks for joining us on this not very cold but kind of chilly January day, as well as thanks for joining us for our first meeting of the 2026 calendar year. My name is Alex McCarthy, and this year I'm going to be the new president taking on. I would like to start by thanking Charles for everything he's done over the last 2 years during his term as president. Real quick, just a little bit about myself and how I got here. I moved to Columbus in 2023, pretty much immediately joined the Columbus Astronomy Society and have been a member ever since. I've served 2 years as treasurer and this year took up the reins as president of this club. I'm pretty enthusiastic about astronomy, so I try to come to as many of these events as I can. I'm also a pretty active member in the Richland Astronomy Society as well, where I'm a board member for them. And there's a lot of great astronomy experiences here around Central Ohio. A couple of goals I'd like to discuss for this year, just with everybody. The two things I'd really like to see CAS really push during 2026 are, number one, expanding our observing opportunities here as a club, and number two, expanding our membership, finding new ways to do that. So over the next couple months, a couple things that I think everybody's going to be able to see is a continuation of what we started last year with some of the periodic club observing nights, and we're going to talk about one of those here in just a few minutes. Also, some of our club members in this room are also involved in CASIS, which is our imaging special interest group. We're also looking at starting 2 other special interest groups within our club. One is going to be an observing special interest group where we'll get together once a month to actually go out somewhere and do some practical observing or some telescope repairs inside if the weather's not going to permit that. So hopefully we'll give people a chance to really learn about telescopes, how to repair and maintain them, and how to really push the limits when out and observing. Once we get that up and running, the other one that we're talking about trying to start is a citizen science special interest group where we get together and we try to push various projects with some sort of scientific value. One of the concepts that we discussed tonight was trying to map and assess light pollution in Central Ohio to see really where are our good spots, where are our bad spots, and there's just some nice science that could go along with that. In terms of increasing our club membership, one thing that we would like to really start to do a little bit better is some social media outreach and social media management with the club. So if you don't follow us on social media right now, please do so, and we're going to look to try to be more active on that moving forward. Other thing I'd like to do real quick is take an opportunity here to recognize our current leadership team for 2026. So can I have all of our officers and trustees please stand up around the room right now? These are the folks who are kind of leading the charge and leading the direction for CAS this year. So we've got myself as president, we've got Charles as treasurer, Isaac Cruz as vice president, he's currently out of town, and Bethany is our secretary. We also have Mark, Ben, Brad, and Charles is our 4 trustees this year, and Jason Hissong's not with us this evening, but he's our other trustee. Please, or not sure where I was going with that, but thanks for all the time and effort that our officers and trustees put into this club. So next up, what I'd like to do is do our partner reports from Perkins and JGAP. So Don, I'll go ahead and turn it over to you for any updates that you have. We'll give you this, and then here's that.
Thank you very much. Don Stevens, I'm the director here and your host. We are currently in a hiatus from our public outreach programs, but we will be resuming in February. February 6th will be our first Friday night program at 8 p.m. And I do want to try to encourage members to feel free to come out and set up a telescope and show the folks that come to the program whatever happens to be up in the sky and share your love of the hobby with them. It's always appreciated. A lot of folks that come to programs, they really appreciate the opportunity to look through many different telescopes and talk to the folks at the telescopes and that. So please do come and help out with those. Yes, Mark?
I was just going to say, you don't need to be an expert. You just need, if you can point your star or your scope at a star you can see, or even if you can't, we'll help you. And I resent that. No, seriously, what I'm saying is that don't feel like you need to be an expert. A lot of times we're showing like one object to a whole line of people. So if you can hold in your memory maybe a couple tidbits of information that that one of us will convey to you immediately beforehand, and remember it for about 30 minutes, then you're good.
Right, or you could just point at something and make stuff up. No one will know the difference. No. So yeah, again, try, if you got nothing to do on a Friday night, you want to come out and help, that's appreciated. We do got a couple of extra telescopes as well if you don't have your own. And we tend to, we'll pair you with somebody who knows what they're doing. Do try to help out with that. I'm possibly going to be organizing like a couple of workshops myself for new telescope owners later in the spring. So watch announcements for that. I've done it a couple years in the past. We do charge a little bit of a fee for that. So I'll make an announcement once that's all worked out as far as how we're going to do it and things of that nature. So if you just got a telescope for Christmas and you want to learn the basics, the class is geared towards basically that, learning your telescope and the care for it and some basic observing techniques and things like that. So again, watch for an announcement around that. I'm working with the administration right now, trying to get some of the maintenance projects back on their radar, to get some of the things taken care of at this place. So, unfortunately right now we got a single restroom to deal with for these programs, and I know it can be a pain having to wait your turn. So I'm hoping eventually get the ones down in the basement repaired so it can open those back up for you guys to be able to use as well. So I'll keep you posted on how that plays out. I think that's pretty much it. So,
Beer.
oh, I'm sorry, what?
The beer.
The what?
The beer.
The beer.
Yeah, you said the non-alcoholic.
Oh, someone, yeah, I don't know where that came from.
It came from us.
Oh,
Just
okay.
wanted to get rid of it.
Oh, okay.
No.
Yeah, can't really have, even though it's not alcoholic, still can't have that kind of stuff here without university permission first. So I put it back in the back room. So if you want to take it with you when you go.
So you're drinking it after this meeting?
It's not alcoholic, but still, the point is. So
So I have a quick question. You have public nights, you open the dome.
yes,
Really?
yes. Yep, during public programs Friday nights.
Okay.
Yeah. All right. Anybody got any questions about that? About the observatory or anything like that? All right. Then.
Thank you very much, Don. Next, we'll turn it over to Brad Hoehne for a John Glenn Astronomy Park update.
Thank you. We have the wintertime experimental reschedulable Night Under the Stars planned for next Saturday. By the way, if you don't know, that acronym reads out as We Are Nuts. It was named that because we do it in the winter, and standing around in the cold at night is not always a great idea. Yes?
Did you check to see if that was already, copywritten?
Copywritten. If it's already copywritten, I'd probably beat them, and I could probably get a little bit of money out of it. So, so that is Saturday, January 17th at sundown, if it's clear. I will be putting out an announcement on the listserv the day before to let everybody know whether or not it's going to go forward the next night. I'm going to do my best to judge what the weather will be like. Currently, the forecast doesn't look good, but of course that's a week from now, so we're probably going to go through several different refinements of that particular forecast. The backup weekend is the following week, so if that doesn't work out, the reschedulable part. If that doesn't work out, then the next weekend we try again and go through the same process. So I will be posting Friday evening probably on the listserv, so you wake up on Saturday morning all bright and early to find out whether or not we're actually going down there. The conditions are currently very good at J-Gap. There is no ice on the plaza. If it snows, typically we do get a plow person in to take care of the driveway. That's just standard for the region. However, the plaza itself cannot be plowed. So if you want to bring your own plastic shovel, please, you can shovel out an area or bring a tarp or something like that in order to observe from. Typically, we don't get a lot of snow. The warmth of the plaza tends to keep the ice off under most circumstances, unless it gets really cold and a lot of snow. Other than that, our programs start back again on March 7th. We're actually doing it kind of weird. We're starting it on Friday, March 7th, and we're skipping a date because in their infinite wisdom, the organization that I am a part of planned their annual dinner on the next night, and that is the organization that runs the plaza, the John Glenn Astronomy Park. That's what it's called. And so we're doing it one day and then skipping the Saturday and then going to regular programs thereafter. They do not take place if it is cloudy. Finally, I still have a few of the calendars if anybody would like to buy them. It's still early in the year and worth your while. They are $20 each, and the funds go to support the programs. So thanks.
Thank you very much, Brad and Don. In terms of our special interest group reports, for Cassis, Isaac Cruz continues to be out of the country for the next 2 months, so there will be no Cassis meeting in no Cassis meeting in January or February. They'll get back together in March, and they've got some pretty good programs lined up once that gets up and running again. Next, I'd like to turn it over to Joe for some outreach updates and any new member updates.
Yes,
sorry.
Could you hold that for me?
Absolutely.
Okay, we do have one guest here. That's Carrie. Would you wave to us? Welcome, Carrie. What brought you here? Would you like to say anything about yourself?
I'm Gary,
Yeah, okay, that's fine. If that's all, that's fine. But welcome, Gary. Good to have you with us. And the next thing is we have some outreach events coming up that we need some help with. The most recent one is going to be next month, February 17th. It's a Tuesday evening. It's at the Columbus Girls School. If you are inclined to help out with that, I have sign-up sheets that are going to go around. The other one is May 2nd, so that's a ways off yet. That's a Saturday night. And that is at Johnstown Community Sportsman's Club. That is a Cub Scout event. And then the third one is at Flint Ridge Nature Preserve and Newark Earthworks, which is a date yet to be determined, but sometime in the spring or in the summer. So I'll pass these around. If you are so inclined to help us out, please give me your name, phone number, and email. Okay?
Thank you very much.
Thank you.
Got it. I want to turn it back over to Brad real quick for an announcement he has.
Yeah, I just a couple days ago, I received a notification from somebody saying that a exchange student organization in Columbus is looking to find a host family for a young woman from Belgium. And she is very interested in astronomy and studying astronomy. And they reached out to me because they thought I might know of somebody that's really into astronomy that would be able to host an exchange student. If this is something you are interested in, drop me an email. I can get you, or just come up to me and I'll give you my phone number and I'll send you the info, and you guys can make contact and see if that's something that would fit for you. So thanks.
Thank you very much, Brad. I think that's the end of our regular agenda before we switch over to programming, but for our other officers here with a little more experience in this club, did I miss anybody? All right, I'll take it. Well, tonight we are joined again by Brad Hoehne giving us our presentation tonight on comets and a lot of the science, myth, and folklore behind them. So anytime Brad's given a presentation in the past, it's always been a good one. We're looking forward to tonight. So I will turn it over to you.
Okay, I'm gonna take over the microphone here. Everybody have pads for their chairs, and you guys know about that. Let me, let's give it another start, an hour to go. Okay, that's good. Okay, guys. So the way this talk came about is Isaac Cruz, the new vice president of the club. He's tasked with finding people to do talks. Last November, we sat around trying to, decide who would be good candidates for the various positions, and Isaac said, I'd love to be vice president, and let's start scheduling the meetings. And he said, does anyone want to do January? And I said, yeah, I could do January. And he said, well, what are you going to do? And I said, what do you want me to do? And he said, we haven't had a talk on comets in a while. And so that's why I'm doing a talk on comets, is because he asked me to. So I went out and learned a lot about comets and used some of the knowledge that I have. So let's talk a little bit about comets here. This is a picture that I took of Comet Tsuchinshin Atlas earlier this year. Does anybody see anything curious about this particular picture? It looks like it's during the daytime, right? Does anyone know why this particular picture looks like it was during the daytime? Because it was a very bright, nearly full moon when I took the picture. And so if you take a photograph of the night sky and the light is just the light from the moon, the sky will still look blue. You're still getting the sunlight, you're just getting a lot less of it. This is about an 8-second exposure of Comet Tsuchinshin Atlas, and it was visible pretty easily in binoculars, barely visible to the naked eye. And for countless millennia, maybe I should turn off the light so you guys can see this a little bit better here. Is this the right one? Is that okay? So for countless millennia, other people had the same experience. When I went down up to the Delaware Dam to take that photo of the comet, I could barely see it. It was just this nebulous object floating in the heavens, just barely there. It tickled my brain in a strange sort of way. It was not a clear object. You look at a plant, you look at a rock, you look at the sun or the moon. They're there, they're clear. Comets, for most of our existence, have been these strange, nebulous objects in the night sky, and they've kind of mystified people in a way. I mean, you're not getting a good grasp of it unless the comet is exceptionally bright. And so people have long ascribed various and sundry aspects to comets because they're a little bit hard to understand. They're a little bit hard to actually see what they truly are. We nowadays have the benefits of photography that can gather light for a very long period of time and give us very, very detailed images of comets. All but the brightest comets are exceedingly faint and tickle our eyes just a little bit. And so humanity's impression of a comet basically started with, hey, there's a fuzzy little object in the night sky. So I'm going to start off and go through the stages of understanding that humanity has had when it comes to comets. And the first stage is, there it is. So we have records going back a very long way that people have seen these fuzzy things in the night sky. This is a set of drawings from around 200 BCE, roughly, from China. You can actually see some of the early proto-Chinese characters there, drawing pictures of comets. These are people actually trying to get a grasp. You can see that they don't really look a lot like comets. They're kind of not really seeing what they are. They're doing their best with these fuzzy, indistinct objects to understand them. I don't get the swastika thing, but that's just how the guy, whoever drew it, interpreted it. So this is from China. China has a lot of very good records on ancient comets. a good way to get a grasp of what people think of something or thought of something is to figure out the etymology of the word we use to describe it. And the word comet actually comes from the Greek Comets, and I'm not a Greek scholar, so I'm probably pronouncing that wrong, meaning long-haired star. And so the very earliest people actually looked up to it and basically thought it was something akin to a star, a long-haired star. And this word actually dates back to 500 or 600 years BCE. So it's been a long time that this word has been part of our lexicon. But the records of comets actually go back even further than that. This is an oracle bone, and this is something that in the eastern, in Asia, on China down into the Vietnam era, up into Korea and that kind of thing. This was a tradition that was a very long tradition. These things go back about 8,000 years. In fact, the oldest name that we know of, the oldest name given to somebody was written down on one of these oracle bones. For thousands of years, people inscribed various things onto oracle bones. And this, and it's very hard to see here, has actually been attributed to an apparition of a particularly bright comet. And this is an early, one of the earliest pieces of evidence that someone has actually seen a comet. So dating to about 1250 BCE. So it goes back a long, long way. On the western side of the world, or the western side of the Euro-Asian, Africa agglomeration of land, I guess continents, the Babylonians were also really good at writing down comets. This is from a set of tablets called the Mul Apin, and they keep very accurate records of a number of comets, and this is one that we now attribute to Comet Halley from 164 BCE, and I think it's right about here that the record of the comet starts on this particular tablet. This is just a list of various astronomical observations, and the comet is right around in there. Right around the same time, a little bit after that, the Chinese started to refer to comets with specific names. They had a number of different names depending on how the comet kind of looked. So the most common name, and I am not a Chinese speaker either, but I know that if you have the circumflex that goes down, you have to go down, and if you have the one that's horizontal, you have to go flat in your tone. So I will attempt to pronounce Xiaoxing. Is broom star. That means a star that looks like the shape of a broom. That's what they thought. And then the circumflex that goes up is up. So you go xiang xing, long star. I mean, a star that is extended. And then yu xing. Xing means star, by the way. And then the little prefixes there are the descriptors. And here are a few more drawings from around 0. That's about the time that these drawings are made for candle flame star. So people actually did recognize the existence of comets for a very, very long period of time. We've known about them for quite a while. So once you recognize that there's a comet in the sky, you start to ask questions about it. And people weren't particularly scientifically minded for a very long period of time. So they were actually they were less interested in knowing, what is that thing up in the sky? I want to know its scientific properties. I want to know why it moves across the sky like it does. More to the point, they wanted to know why it's there in the first place. And this drawing, which was probably made about 1,000 years ago, but depicts something that occurred about 600 years before that, roughly in the year 400 or so, is a record of a disaster that happened in Europe. It was a set of great fires and plagues and that sort of thing that happened, which people ascribed to a comet. Here's the comet. Do you guys see what's wrong with that particular comet? Yeah. Okay, the tail is pointing down toward the horizon, although it could just be a really, really bright comet and the sun is up over here somewhere, which I don't think is what happened. But this is pretty on par with what people thought about comets for a very long period of time. So let's take a look at some of the philosophies of what people thought about comets. First of all, why do people think comets are associated with disasters? First of all, let's take a look at the movement of the planets. So these red lines on this picture are the paths of the planets. I also included Uranus and Neptune just for fun. But this one up here, that's Mercury, a little bit further up. This is the paths of the planets across the sky. They all hover near this orange line, which is known as the ecliptic. That is the imaginary path through the sky that the sun would appear to take if we could actually turn off the sun and just see where it moves across the stars. That's an artifact of the orbit of the Earth. Our view of the sun changes as we go around it. All the planets are still roughly in the same orbit because of the cloud of gas and dust that the planets formed out of. They all seem to be roughly in the same plane. Mercury tilts up just a little bit. It's tilted a little bit more than the rest of the planets. But by and large, they're fairly well behaved. They pass through the same superhighway in the sky that the sun and the moon appear to pass through. So they're well behaved, very predictable. It was kind of easy to know, okay, Jupiter's over here, it's going to be over here next year, it's going to be over here next year, it's going to be over here next year. So I took one particular comet. This is one that is going to be fairly bright at the end of the month. And I plotted its orbit over the next couple of years. As we will see it, you'll notice that it doesn't follow the ecliptic, first of all. And second of all, it does kind of do a little whirligig. Now the planets do this as well, but when they do it, they tend to stay within the ecliptic when they form that little whirligig motion that they do. That's because of the motion of the Earth around the sun. We actually see the comet from different angles, and it makes a little loop-de-loop. So this is about a 2.5-year cycle of this particular comet in the future, not going along the ecliptic. And since to the ancients, the heavens were somehow pristine, somehow divine, somehow otherworldly, and these things, comets, come in and kind of break down that system, they must be portents of doom. There must be something wrong with the heavens when a comet appears. So Chinese were also into this. They also thought that they were portents of doom. This was spread largely all over the world. In the Wu Xing, remember Xing is star. This is the yin-yang symbol. To the Chinese, a comet would knock the yin and yang out of alignment. You needed a certain amount of yin energy in the universe, a certain amount of yang energy in the universe. And when they were in balance, everything was harmonious and things were good. But comets threw that out of balance. And so to the ancient Chinese, it was also something bad. And to prove that, we have this particular emperor, and I will mess up his name, is Ruzhong, from the early 8th century. This guy saw an apparition, or had an astrologer see an apparition of a particularly bright comet in the year 712. And he promptly decided that his days were numbered, and he abdicated. So he basically said, I'm not going to deal with the mayhem that is going to ensue. I don't want to die, basically. I don't want to get overthrown. I don't want to lose battles or get blamed for it. Just go and retire in my lovely country estate with my 300 concubines and enjoy life, So So in the Western world, philosophers also had a number of things to say about comets. These particular writers, many of them you've probably heard of, Homer. These two guys were Greek, Seneca and Gaius Suetonius Tranquillus, which is kind of an ironic name in this case, all wrote about comets, and they all had the same philosophy on comets. Comets are bad news. They were portents of doom. They foretold the loss of battles. Generally, they were involved with some sort of leadership philosophy. If you had a comet come into the sky that was particularly bright during your reign as emperor, you were probably going to experience some bad news. Now, here's the thing. If you were a Roman emperor, you were probably going to experience bad news anyway. Not many of them lived all the way until their natural lifespan. But yes, comets were blamed for much of this. And so it was fairly widespread. Once again, this is the recounting of a 4th century comet as seen in Europe. This particular philosophy lasted quite a long time. So we're going from the Roman era into the modern era. And let's fast forward all the way to the 17th century when this particular natural philosopher in Germany wrote a pamphlet when there was a bright comet seen in 1618. He was the alarmist of his day and thought that all sorts of things would come to pass as a result of this really bright comet. You can see that he expected to see earthquakes, flood, droughts, hailstorms, bad harvests, plagues, treason, and inflation. Yes. So, given the fact that this is happening in the early 17th century, one could argue that perhaps those things would happen anyway. But yeah, even up to the 16th century. This is after Galileo pointed his telescope at the heavens and after the Copernican model of the universe was starting to take hold here.
Conspiracy theory.
Yes. So it took until around 1700 or so for people to stop kind of believing that comets were portents of doom. Some people held on for a while. But this is the Royal Society, and they kind of figured out that, comet or not, bad things tend to happen. Kings die, battles are lost, plagues happen, and they happen if there's not a comet in the sky or there is a comet in the sky. And so they went back through the records and actually compared the way things were working, and comets didn't seem to have any impact. And so they grew, at least in the scientific realm, a little bit skeptical. Now, some rulers had people on the payroll. In fact, one Charles Messier, who you may have heard of, was on the payroll specifically in order to find comets. And why was he asked to find comets? Well, because the king was still interested in knowing whether or not there were comets in the world. So you could still make a name for yourself as a protege of the king as a beneficiary of the king's largesse if you were a comet hunter. So I'm going to look at this, Alex, and just see whether or not, I still should have a few minutes. Let me here. So people got a little bit skeptical at that point. However, we still have people that hold on to the belief that comets are kind of unusual. This is kind of a case of a quote that was never really said by the person who was said to have said it. You know how Albert Einstein or Abraham Lincoln is said to have said many, thousands of different things. He said, "Use the Force, Luke," or something like that. So in 1910, a particularly close pass by Halley's Comet, a particularly bright apparition of Halley's Comet. That was the previous one to the one that took place in our lifetime. And this particular French natural scientist, who's a little kooky on his own, was a bit concerned about the cyanogen gas that had been found in the tail of the comet. By then, the spectroscope was in use, and people were able to analyze the constituents of comets. And he said, cyanogen gas will impregnate the atmosphere and possibly snuff out all life on Earth. Except he didn't say that. He said something along the lines of, it's vaguely concerning that there's some cyanogen, but this is something we'll look into, and people took that and panicked. And it became kind of a cottage industry to sell various and sundry things to ward off the cyanogen gas that we were all going to get poisoned from. And this is an actual bottle of Comet pills. And this was a pamphlet from a ladies' magazine that was telling you how to avoid the comet gas.
Do those pills contain mercury?
Yeah, I probably, that sort of, maybe some arsenic or something like that. Yeah. But yeah, they were probably just sugar pills. But yeah, they sold Comet pills to ward off the cyanogen. Sold a lot of gas masks and that kind of thing. But this was way back in 1910. Surely we have gotten better since then, yes. Yeah, but we still have a certain subset of the population, which is distressingly large, that does tend to believe that a certain comet foretells some sort of doom. I mean, how many people saw social media posts within the last year or so saying that the Comet 3I Atlas, which is coming in from outside the solar system, was somehow some alien spacecraft that was going to wreak havoc on the Earth. I blame this on this guy. Anybody know who that guy is? It's that Harvard astronomer. Yeah, his name is Avi Loeb. He never made an alien suspicion that he didn't like, but he has tenure, so they can't fire him. So anything that just happens to be like, scientists think this may be aliens, probably this guy. So, okay. So in any society, people have strange beliefs about comets. But it's taken us a very long time to get the scientific understanding nailed down. So let's talk a little bit about, one more thing. Not all mythologies and attempts to understand the why of comets have been 100% negative. This is the Norse god Ymir, if I'm pronouncing that correctly. Ymir was killed by Odin, and Odin's brother. He was there at the beginning of creation and was killed. And according to Norse mythology, the body of Ymir, the muscles of Ymir became the land. His blood became the oceans. His skull, the inside of his skull, held up the sky. Comets were flakes of the skull eroding from the sky and falling down at the ground. And so I think that's kind of cool. That's pretty bad. That's a better story. Yeah, that's a pretty good one. So the Norse, the Vikings, man, they got a real Klingon way of looking at things. It's all about the death of some god with a big set of horns on it. I'm sure that this is an AI rendering that I stole from the internet. But so not every single philosophy, but surprisingly, across most of Eurasia and Africa, comets were considered to be portents of doom. It was a very common, even in the Americas. Montezuma was said to have been alarmed by a comet. And perhaps this led to his downfall because he was predisposed to be a little distressed about the coming European invasion.
Who's the character on the other side?
The character on the other side?
The skull.
The skull. That's his skull.
Oh.
Yeah, that's his skull dissolving away. This was just a Photoshop job that I did. So, okay. So let's take another step in the understanding of comets. If you don't know what comets are, you can still kind of try to figure out how they behave in the sky. So the next step in understanding comets is to figure out precisely where they are and how to define that. This here is a map, by the way, made by Mr. Charles Messier of a comet. This trail right here is all of his observations of a comet. The reason why we actually have the Messier catalog is because he was initially interested in observing comets. And he was hired to do this, to look for comets, not because he was a particularly great astronomer, but because he had really good handwriting. He made this map with his own hand, and you can see he's got really good handwriting. And since he was such a good cartographer, they decided, you know, he would also be at least as good of a celestial cartographer. And so Charles Messier switched over to astronomy and started hunting down comets, and eventually ended up accidentally running into a number of not comets, things that did not move like comets do, and the rest is history, and we get the Messier catalog we know and love today. But we also have a lot of these lovely maps of some of the comets that he spotted. One of the comets that he really wanted to spot was, of course, the return of Halley's Comet that had been predicted about around the year that he started to observe. And that's kind of what really got him into it. He was actually attempting to do that specifically in order to prove that Halley had actually made an accurate prediction as to its return. But our story once again starts back in the past. The Chinese, once again, kept very good and accurate records of the positions of comets. They have a set of records that are called shijir, which basically translates to historical records. And this is a set of observations of one particular comet around 240 BCE. That particular comet, it turns out, happened to be this one, Comet Halley. And it's really helpful to look at those records because they had maps of the sky and would relate the positions of the comets that they saw to the stars that they had mapped in the sky. They would say it's between this one and this one, 2/3 of the way or whatever. And they would observe, they would take down records in that way. And we could recreate the positions based on their verbal descriptions of where these things were. And it turns out that it's accurate to about a degree. And this has been very helpful to future scientists in nailing down the origin and the paths of some of these ancient comets, because the Chinese were so good at it. Another good source, turns out, it happens to be the Anglo-Saxon Chronicle. The Anglo-Saxon Chronicle was compiled. It's a big historical chronicle of the various goings-on in the British Isles, mostly in the English part of it, starting around the early 7th century. However, they did not just note battles and kings and lords and such, and various religious festivals and events. They also noted happenings in the sky. Turns out that the Anglo-Saxons were pretty avid sky watchers and kept pretty good, pretty accurate records of comets and how long they lasted. This particular comet that happened in 678 AD, appeared in August, lasted 3 months. Somewhere on this page, and I can't find where it was. But it happens to be on that page, and there's a drawing of it. These historical records also include notation of comets in various other historical records. This is the Bayeux Tapestry, which is a very long tapestry that was sewn to commemorate the Norman invasion of England and the overthrow of King Harold in the year 1066. During that year, there was an apparition of Halley's Comet, which they actually include right here in the Bayeux Tapestry. So they kept a record of that as well. So we have a record that Halley's Comet in fact appeared in needlepoint. So people kept good and accurate records of the positions and the movements of comets. But people didn't really have a very good understanding of why they moved the way they did. Until this guy. This is Johannes Kepler. And Johannes Kepler was extremely interested in the motion and orbits of the various planets. And he was an early devotee of the Copernican model of the solar system, which put the sun at the center. His goal was to somehow devise some overarching system that would allow people to know why the planets were at certain distances from the sun. He wanted to know why the various relationships of the distances between the sun. Instead of that, however, he figured out a system not of why, but of how to predict the motions of the planets. He did this primarily by looking at the motion of the planets in the sky and was able to figure it out more or less because of the curious motion of Mars. Mars's orbit is particularly out of round, and it deviates from a perfect circle by a not insignificant amount. Enough that if you tried to model the orbit of Mars as a circle, it wouldn't be a particularly good model. To the accuracy of measurements that he was using, which came from Tycho Brahe, he was not able to figure out a circular orbit that matched those positions. Well, a lot of math ensued, and around 1619 he had come up with a complete set of rules for how how bodies in the solar system behave, and let's go over those. Here's another body in the solar system, which you can see does the same little loop-de-loop, and this is the type of thing that he is explaining. So let's go over his rules. First of all, he figured out that comets do not. I will stop if you want to start again. Okay. We're recording. Is the red light still now on? Good. Okay, excellent. Thank you. So he eventually had to give up the idea that the planets actually moved in perfect circles. This was something that since the time of Aristotle, people had long held that the planets moved in perfect circles to a degree. They also had the idea that if they didn't move in a perfect circle, sometimes they would move in little offset. They would move in a perfect circle, but it would slightly be offset from the sun at one focus. Kepler actually figured out with very detailed mathematics that the planets actually move in an ellipse, particularly Mars. Mars has got a particularly elliptical orbit. The sun is at one focus. An ellipse is a body, or a figure that actually has two focal points. And if you want to draw an ellipse, you actually can take a string, put it around the two, and then run a pencil around here. And then the one focus and the other focus actually define this egg-shaped figure. The further apart the pegs, the longer and thinner the ellipse will be. So the sun is at one of those two focuses. So that's the first law that he figured out. The second law that he figured out, so here's an ellipse. I was going to talk about that. So here's one focus. This is the other focus. And if you figured out the distance between this, and this, focus one, the side of the ellipse, and focus two. If you ran a pencil around here with a string, it would always follow the path of the ellipse. So the string has just got enough slack to go a little bit further past this end on this side, and then here it's got enough slack to only go out about this far. So when an ellipse is actually quite long, the focuses actually get really, really close to the edge. The ellipse is actually divided up. We measure the length and the width of the ellipse in terms of what they call the major axes. This is, or excuse me, the axes. The semi-major axis is 1/2 from the very center of the ellipse to the edge. That's the semi-major, 1/2 of the major axis, semi-major, and that's the one that astronomers use a lot. And then the semi-minor axis, this is the minor axis, the thinner side, and the semi-minor is half that. So this is the features of an ellipse. Now the center doesn't really have anything to do with anything physically. There's no body at the center of an ellipse. The sun would be here, and whatever it is that is orbiting the sun, be it comet or satellite or whatever, is going to be orbiting in a giant ellipse, sometimes getting very close and sometimes getting far away. You notice that this ellipse is not particularly long, but it's actually drawn to scale. The focuses actually get pretty close. So even though this is not squished out like a pin, the focuses are still pretty close to the end of the ends of the ellipse. So his second law that tells you not just where the objects move, but how fast they move, is that as the body goes around the sun, it actually sweeps out equal area in equal time. What does that mean? That means that the area of this triangle, this circular wedge right here, is the same as this area. So if this has got a much longer baseline here, the body's going to be moving a lot slower out here because it doesn't take as much of a sweep for it to produce a large area. And this is going to be moving really fast because it's a lot closer, and this length right here is not all that long. So that defines how fast the bodies move in their orbits. Now you still need some baseline. You still need to actually figure out, like, what are the periods of these bodies. I mean, you could have, this ellipse could be 1 AU semi-major axis, 1 Earth-Sun distance. Or it could be 100 AU, How do you define what the times are of the actual orbits? Well, his third law defines this. It is that the time of the orbit squared is proportional to the length of the semi-major axis. So if you figure out the length of the semi-major axis of any of the bodies, for example, the Earth, we know that the length of the Earth's orbit is 1 astronomical unit, or the semi-major axis of the Earth is roughly 1 astronomical unit, because our orbit is very, very circular. And we know how long it takes the Earth to orbit the sun, 1 year. We can compare everything else to that. So if something has a semi-major axis that is twice that of Earth, so twice that of Earth, 2 times 2 times 2 is 8, it is proportional to the square of the time of the orbit. So it would be the square root of 8 would be the time of orbit of something that is twice as far away as the Earth. And the square root of 8 is 2.8, something like that, 2.7, somewhere around. Anybody do math in their head really well? Somewhere around in there. It's not 2.5 because that's 6.25. It's not 3 because that's 9. So it's 2.7 or 2.8 or something like that. Just doing back of the envelope calculation there. So this gave us a model for how planetary bodies move about the solar system. Now, Kepler was using planets as a model. However, this guy, Isaac Newton, came along and figured out why the bodies move that way. He devised the universal law of gravitation, and this particular equation, which is the force on a body is equal to some constant times the two masses divided by the distance between the two bodies squared, And if you run a system with those particular forces, you will actually get the Keplerian orbits. You will get an elliptical orbit if you run that with Newton's law. So Newton actually kind of figured out the mechanical model by which Kepler's system actually works, but it took Kepler to figure out that planets actually have these particular orbits. Turns out that comets are very easy to predict using this system. You can predict comets with Keplerian orbits, just like you can predict, the planets as well. At the end of the 17th century, people had started to predict the motions of planets, or excuse me, comets. And one of those people was this guy who did not discover a comet, but he actually went back through some of those historical records, and in particular noted 3 apparitions of a particularly bright comet that happened in 1531, 1607, and 1682, each of which is about 76 years apart, and noted that if you go back in time, about every 76 years, there's a comet. And he did the math, figured out that this was probably the same comet. He was using Newton's formulas. This took place, Newton's Principia was published in 1688, and he did his prediction in 1705. And Halley died before the next comet apparition was to take place, but it turns out that Halley's comet was exactly in the place that he said it would be. And so it was determined that yes, comets do follow predictable orbits, and there are comets that come back time and time again. Halley's comet is now called Halley's comet because Halley was the person to figure out that a bunch of these comets that were particularly bright were all the same one in time. And people were a little bit skeptical. You know, they thought, maybe it's just, maybe you were just lucky that there were comets in that year. And so he wrote a kind of distressed note saying, I must entreat you to procure of me, Mr. Flamsteed, that he has observed the comet of 1682, particularly in the month of September, for I am more and more confirmed that we have seen that comet now 3 times since the year, I love how he spelled year, 1531. He will not deny it to you, though I know he will me. So basically, he's getting somebody else to do the dirty work for him because, people didn't really believe Halley, but they will believe some other esteemed astronomer. And so eventually, Halley actually got the renown he was owed for his observation. But at first, people were somewhat skeptical about it, and it required a little bit of underhanded dealings for it to be more accepted within the scientific community. So let's take one particular comet here. This is a comet that's actually up now. This is one that we could perhaps see. It's roughly in 9th magnitude or so. When this picture was taken, it was around 11th magnitude. This is comet 24P Shalmazi. 24P is a periodic comet that comes back time and time again. And let's take a look at what you normally experience when you are looking for the position of comets in a chart. If you want to know where a comet is going to be, people actually now publish predicted positions of comets. And you get these things. These are called ephemerides. Am I pronouncing it? Ephemerides. Ephemerides. I've heard a number of different ways of pronouncing it. Ephemerides. And this right here is typically what you get. If you want to know where a comet is going to be on a given date, you'll notice that right here on the left we've got the date. The delta is the distance from Earth. Delta just means a change between 2 objects. R is the distance from the sun. That's short for radius. Elongation from the sun, That is how far in degrees it is from the sun in the sky. So if something has a great elongation, this is a pretty good elongation, 94 degrees. So that's a quarter of a way around the sky. So that's a good comet to watch. So it's not going to be hovering in the twilight. This is its magnitude as of last week, around 8th magnitude. And this particular ephemerides has a best time to observe it, 5:38 in the morning, and at the where it will be in the sky and how high it will be up. This is its azimuth, 340, and that's its height above the horizon, 68 degrees. So this is a really good comet to see right now because it's really, really high up in the sky. The last thing that we need to look at here is the epoch. When you measure the position of things in the sky, you need to give the epoch that you are measuring them against, because the coordinate system that we use here on Earth slowly changes. So if I were to say that this particular comet is in a particular region of the sky in the year 2000, according to the position of the sky in the year 2000, if I took a chart from the 1950s and attempted to plot the position of that comet, it would not be in that spot. And the reason why this is because the Earth wobbles slowly, like a top. Every 25,800 years, it makes a complete wobble of its axis, causing the position of the celestial coordinate system relative to the stars to shift. And so what we need to do is we need to nail down what coordinate system we are going to be using, how we are going to be measuring this against the stars. And we need to pick a particular time and position of the stars in order to do that. And in this case, the epoch is 2000. Usually they go in 50-year chunks. So sometime within the next 10 years or so, we might start using the 2050 epoch, because we're going to get a little bit closer to that. It's going to be a while. You might get star charts that are printed, if people still print star charts, in the epoch 2050 next. So here's, once again, 24P Shalmasi. And so if you have the positions of the comet plotted out, let's say you're an observer and you've just discovered a comet, you want to know what its orbit is. But all you've got is a telescope and a way to figure it out where it is in the sky of the Earth. So all we've got is the ability to see the comet is here one day, here the next, here the next. If we know where it is in the sky, and we know precisely the time at which we made the measurement, we can actually figure that out. Now, I did a little talk on special relativity last year, last January in fact, where I did some of the simple algebra of special relativity in order to show you that special relativity is something that someone in high school could understand, mathematically speaking. The math for figuring out the positions of a comet in the sky, given simple observations from a moving platform, the Earth, is really, really difficult. I actually did this a long, long time ago. It was hard then. I rewatched some videos this month. There were like 23 steps to the whole thing, and it involved matrix algebra. I'm not going to do it. I'm just going to tell you the gist of what is done. The method was devised in 1801. It was kind of a trial and error system until then, but Gauss actually figured out a clear way to take, to take just 3 observations and turn them into an orbit. That's all you needed, 3 observations at given times. you were on a moving platform, you needed to figure out, you plug it into Gauss's system. You go through a whole lot of different calculations. Once again, the tutorial that I watched had 23 steps and matrix algebra, and my head was bleeding at the time. That gets you the position of the comet in 3D space from 3 observations. Now you need to fit that to an ellipse. You actually need to figure out to fit that. There is a modern method for fitting that to an ellipse, and it's called the Gibbs method, which is also really complicated, and I won't go into. But just suffice to say that the Gibbs method allows you to convert it into an ellipse, and Gauss's method allows you to figure out the position of the bodies. But it's a little bit difficult. So here's the two. You have to know. It helps to know that the movement is an ellipse. You need at least 3 position and time measurements. More helps because as you do this, as you make measurements, any measurement is going to have some sort of inaccuracy to it. If you have more measurements spread out over a longer period of time, you will get a more accurate. Ellipse. Yes, go ahead.
Question.
Yes.
There was a precursor to calculus. Things were all done graphically.
Yes.
Do you know when that timeline took place?
So calculus, Newton devised calculus.
Right.
In the Principia, actually, and the end of the 17th century, roughly. That was when Leibniz and Newton actually devised it. So Kepler actually all did this with, long-handed calculations. I mean, he actually was able to figure it out kind of just by trial and error, sort of fitting the curves manually and trying to guess what would best fit. Gauss actually figured out an actual system for figuring out the true positions of the objects, and Gibbs extended that to allow us to figure out, exactly what ellipse we were talking about. One thing that's very important is you actually need to know the motion of the Earth. So you need to subtract that out, because when we make these measurements, I make a measurement on March 5th and April 1st and May 2nd and watch this comet. I'm on a moving platform. I'm actually seeing it from 3 different places. So it's actually very difficult for you to figure out where this comet is in the sky. It helps to know exactly what Earth's movement is, and we had to figure that out. And it also helps to know that the movement of the comet is in fact an ellipse. So you fit those 3 measurements onto an ellipse given those 3 points at specific times. They use what's called finding the best fit curve. It's a system for actually kind of whittling down all the possible positions to find the best possible ellipse that fits the observations that you are given. And actually, you don't have to do this nowadays. You can actually, you can download these Python libraries that do this for you. And you know what? I think I just knocked off the microphone. No, I didn't. Okay. So you can download these Python libraries that have all the math built into it for you, and so you don't have to figure that out yourself, which is really, really nice because somebody else has done it for you. And unless you want to get a degree in matrix algebra, it's really complicated. So once you've figured out the ellipse, this is what you get. You get what are called the orbital elements. Is that still going?
Should be.
It should still. Okay, thank you. Okay. You get the orbital elements, which are different than ephemerides. Orbital elements are a graph of the ellipse, which allows you to predict where the comet will be as it goes around its orbit. It gives you a certain number, a certain characterization of the actual orbit of the comet. So let's go through some of the orbital elements here. First of all, the most important orbital element, the one that's most interesting, I think, is the eccentricity. The eccentricity is how out of round the ellipse is. So a perfect circle, an orbit that doesn't get closer or further away, it has an eccentricity of 0. That's a perfect circle. And an eccentricity of 5 has the semi-major axis, which is double, or semi-major axis, which is double the length of the minor axis. So that is an eccentricity of 0.5. And then an eccentricity of 0.95 is a very extended one. And ellipses actually get really, really long. I mean, you can have something that is indistinguishable from a line. In fact, a lot of comets have orbits that if you were to look at the whole thing, it just looks like a line because it's such an long ellipse. You'll notice that the sun is way, way over here on the side of this really, really long ellipse. And then for the one with the eccentricity of 0.5, it's kind of off to the side. And the one with the eccentricity of 0, which is the perfect circle, it's right in the center. Now, eccentricities can go higher than 1. An eccentricity of 1 is what is called a parabolic orbit. The orbit is, the body is moving in a parabola. These are all what are called conic sections, by the way. If you take a cone, a perfect mathematical cone, and you slice it every which way, you can get, if you slice it straight parallel with the bottom of the cone, you get a circle. If you turn it to the side a little bit, you get a long ellipse, and if you turn it to the side a whole lot, and you get just down the edge, you get a very extended ellipse. If you go straight down, straight down the side, not along the edge, you get a parabola, which has got an eccentricity, by definition has an eccentricity of 1. That is an orbit that is not bound to the sun, but it's not bound to the sun. It's right on the edge of being infinitely large and, not infinitely large. It's right on the boundary of being there. Now, eccentricities can actually get higher than that if something's not bound to the sun, but it's affected by the sun's gravity as it passes by, like 3I Atlas. It'll have an eccentricity that's a little bit higher. I'll show you a couple of those in a little bit to come here. So let's take a look at this little graph. Here's a chart that shows you the different eccentricities, and you can see how the different elements of the ellipse change as the eccentricity changes. So here's an eccentricity of 0 because it's a perfect circle. But if I turn it on, you'll see the eccentricity goes up and stretches out. And once it gets past 1, something very curious happens. The ellipse turns into a parabola briefly, and then it turns into a hyperbola. That is the shape that it forms. So let's go through it. Here's the ellipse getting longer, and then boop, it gets over 1, and it becomes a hyperbola. So this dot right here, that's the center of the ellipse. And once that goes out to infinity, it actually goes outside, and the center of the hyperbola, the definitional point of the hyperbola is actually considered to be over on the other side of that. So you'll notice 0, and then right there 1, and then it gets higher and higher and higher. So as you'll see, as it gets closer and closer to, as the E gets higher and higher over 1, the orbit actually gets flatter and flatter. So that's eccentricity. But there are some other elements. If you know the shape of an orbit, you don't know its position in space. You need to know some other things about that. So the ellipse is going to be floating in space, but it could be every which way. You can actually have it, lined up perpendicular to all the other planets in the sun. You could have it at an angle, but you could also have it tilted either way. And so in order to determine the exact position of this body, this comet, as it orbits around the sun, you need 6 different figures. So first of all, you need the eccentricity. That's the length of the orbit. You need the length of the semi-major axis. That gives you how big the orbit is. So something with a small eccentricity, or a large eccentricity, can be a really tiny orbit that's close to the sun, or a really big orbit that goes way far out, but they can have the same eccentricity. So, something with an eccentricity of 0.5 can be, coming out to the orbit of the Earth, or it could go all the way out to Pluto or something like that. But it would still have the same shape. So those are two figures. The semi-major axis is very important. The position of the semi-major axis is defined by what's called the argument of the perihelion. It's a strange word, argument. But argument just simply means the spot at which this thing happens. The argument of the perihelion is the part of the ellipse that is closest to the sun. And the semi-major axis follows that same line. So the argument of the perihelion is the position in which it's closest. So you define the argument of the perihelion as this direction. The inclination is how much, right over here, is how much it's tilted relative to the plane of the solar system. The plane of the solar system is defined as the plane of Earth's orbit. So, if the comet is tilted relative to the plane of Earth's orbit, we're very self-centered here. We define it by our own planet. Something with a high inclination is going to be roughly more perpendicular to the plane of the solar system relative to us. Something with a low inclination is going to be coming in right around in the same plane as Earth. Then finally, you've got two more. You've got the longitude of the ascending node. That is not the up and down orientation, but the around the sun orientation. It's this way. And then the true anomaly. That's kind of a weird term. The true anomaly is just where it is in the orbit relative to the argument of the perihelion. So you start at the argument of the perihelion with 0, and you go all the way around, and if you get back to this, that's 1. So 0.99 would be right here, 0.5 would be up here. So the argument of the perihelion is basically how far around the orbit it's gotten. Now there's one thing missing. This has to be related to something. And that thing that it is related to is known as the first point. And the first point is defined as a particular direction in the sky. And once again, it is defined based on Earth. The first point is the spot in the sky where the sun would be at the spring equinox. It is the position of the equinox is the first point. So all of these orbital elements are related to the equinox. Now here's the problem. As that tilting takes place, as that wobbling that Earth's orbit does takes place, this position slowly moves across the sky. It wobbles through the heavens. And we actually, if you have the orbital elements of a comet fixed for a particular day, they're not going to be good for another particular day. And we want to know precisely the orbit of comets. We want to know them really, really nailed down. And so because of that, we actually measure the orbital elements of comets relative to the most recent epoch. Like today, if you want to get the orbital elements of a comet, you recalculate them for now, generally, or within the last month or so. So here we go. So in this case, we've got epoch 2025, November 21st, 0.0. And they measure it according to Julian days. This is days from the year 0. 0.5 means midnight. They start from noon in the year 0. That's the number of days that have passed since then. So this is the epoch that they're measuring this whole thing. That defines the first point in the sky. So all of these other numbers are relative to that. So the semi-major axis here is A, typically. They don't usually tell you in the orbital elements what these are. You gotta go look them up. But if you know the symbols that they use, typically A means the semi-major axis, defined in terms of astronomical units. So the semi-major axis for this particular comet is semi-major axis is 4, which means that half of its orbit is 4 AU. So it gets out a little bit further than 4 AU from the sun. Probably it gets about 7.5 AU from the sun in this particular case. But that just tells you how big the orbit is. This has got an eccentricity of 0.7, so it's a pretty round, it's like egg-shaped. It's a pretty good round orbit, so this is not a incredibly long and extended cometary orbit. The inclination is 11 degrees, so it's roughly in the plane of the solar system. The longitude of the ascending node is 78.27, whatever that means, relative to the first point. That's how far the ascending node is from the first point. The argument of the perihelion, that's the position that the angle that is between the first point and where the closest point in the orbit is from the sun. And then this other one, the mean anomaly, that is another term for the true anomaly. That basically means how far around the orbit it's gone. And in this case, they've actually measured it in terms of degrees around the orbit, so 354 degrees. So it's almost back to its closest point to the sun. So in this case, this particular comet was very, very close to being at its closest point because it was near 354. And this particular website that I stole this from about the comet actually had basically what its magnitude was. This thing called slope parameter measures how bright it gets relative to how expectedly bright it gets. It's very complicated, so I won't go into that in too much detail. There's a few other numbers here on the orbital elements. Oh, by the way, up here in the corner, this pike is for a young woman named Rosemary Pike, who is the current international person who actually does the computation for these particular comets and publishes these particular orbital elements when a new comet is discovered. So if you see the orbital elements, generally it's probably gone through her computer somewhere. And this right here is the distance of the periapsis. That's how far away the comet will be when it is closest to the sun. That's another actually one. You don't need that, but it's because you get it from the eccentricity and the argument of the perihelion. But you can. It's a nice little convenient thing that they put in there just to give us to make it so that we don't actually have to compute these orbital elements, this actual thing for ourselves. So this one's not actually going to get closer to the sun than the Earth. It's a little bit further out from the sun. Its perihelion is further from the sun. And then finally we get these extra little elements. These are generally defined in terms of some extra little mathematics that are behind the scenes, and they aren't related to these numbers very much. They are a magnitude of a certain calculation that's done, and they define the magnitude of the perturbations from the other bodies in the solar system, mainly Jupiter and Saturn. Because even though these orbits are roughly elliptical, it turns out that they're not exactly elliptical, because as Jupiter goes around the sun, it tugs a little bit on the comet. Saturn does that too. We do it as well. If a comet were to pass particularly close to the Earth, these perturbations would be affected to a certain extent. And this is simply a measurement of the magnitude of those perturbations in two different directions. P is perpendicular and Q is along the plane of the orbit. And then finally, we have what are called non-gravitational parameters. So if you take the perturbations into account, and yet this comet is still not quite behaving 100% like you would predict. It's not an ellipse that's being perturbed by the planets. You get what are called non-gravitational parameters. They're right here, and they typically are involved with the jetting of the comet. As the comet gets in close to the sun, the body heats up, pushes on acts as kind of a jet that pushes on the comet, affects its orbit to a certain extent. And this is the little bit of extra movement. Similar to this, it's not relative to these, it's relative to some other calculation that is not shown here. But the mean residual right here, that mean residual, is about how far off in arc seconds the comet is from where it ought to be given the gravitational effects on it. So it's about 0.8 of an arc second, which is not a lot, but it's enough to make a difference in certain scenarios. So it's interesting to know. So finally, those perturbations are divided up into A1, A2, A3. A1 is the radial vector. That's how far in and out of the sun it's being pushed. So this is actually being pushed a little bit away from the sun, perpendicular to the sun. North is up. North is positive, south is negative, so A2 is perpendicular to the sun. And then A3, perpendicular to the sun in the plane of the orbit. So that's, before and back. And then up and down is perpendicular to the plane of the solar system. They don't include that because apparently there aren't a lot in this particular comet, so it's not enough to really be interested in. So those are the orbital elements. Astronomers generally divide the orbits of comets into different categories depending on the length of their orbit. First of all, you have short period comets, which are defined by definition as being 200 years or shorter, and long period comets are simply comets that are longer than 200 years. That's pretty simple. Long period comets can be very long. They can go up to something like 1 million years. Orbits can happen. However, as we will see, once you get up to those really high numbers, you're dealing with some pretty nebulous definitions of orbit here. There's another set of comets they call the Jupiter family, which are comets that are less than 20 years. These are typically periodic comets that come around time and time again, and their orbit is relatively short. It is thought that these comets actually made a close pass by Jupiter or Saturn and were captured in the inner solar system and now come back time and time again. There are a number of comets that have like 5-year orbits, for example, that are just kind of tooling around the inner solar system, going out to the asteroid belt and back. And then dividing down the long period comets, there are a not insignificant number of comets that seem to have semi-major axes of between about 40 times the Earth-Sun distance and 500 times the Earth-Sun distance. To just give you an idea, Pluto is roughly 40 times the Earth-Sun distance. So we're talking out around the Kuiper Belt region. But then there are a large number of comets also whose orbits seem to take them out to many tens of thousands of AU, out to something like 50,000 astronomical units. A light year is about 20,000 AU or so, and so 50,000 is about 2.4 light years. That's a huge, huge orbit. So if you go back over time and you look at all of these comets coming into the inner solar system, you see a bunch of these short period comets which come around time and time again, but you get an awful lot of these once in a lifetime comets that come screaming in, if you figure out their orbits, from way far out in the middle of nowhere. How much time do we have on it?
About 10 minutes.
About 10 minutes, okay, good. Are we good? Oh, good, okay. We get these comets that seem to be screaming in from an extremely long distance away. We're talking tens of thousands of AU. And there's quite a few of them. And they have to be coming from somewhere. If you figure out the orbits, it's clear that they are in fact orbiting the sun. Many of the times. Their eccentricities are like 0.9999 whatever. They're very, very long orbits. But they're coming in from a very long way away. And so these two gentlemen, unfortunately this guy named Ernst Öpik didn't get a lot of credit, but he came up with the idea independently. And a little bit later on, this guy named Jan Oort realized that there must be some giant reservoir of comets that are way, way out there, which now today, it seems to be that the comets come more or less from these great distances from all directions. So they're up above the plane of the solar system, down below the plane of the solar system. They're coming from everywhere. So it is inferred, based on this, that there is a giant reservoir of trillions, I guess, of icy bodies that are out there that occasionally get nudged and fall into the inner solar system. And it is called today to commemorate Jan Oort and kind of not commemorate, unfortunately, Mr. Ernst Ippich, the Oort cloud. Now, those short period comets that go out to like 200 years or so, the ones that have very long orbits, some of those actually take them out specifically out to a point that's kind of just a little bit beyond Pluto. And this region has long been inferred to be also another reservoir of comets, but that particular region tends to produce comets roughly in the plane of the solar system. You know, there's some above and some below. I mean, Pluto is tilted quite a bit. But the comets that come from between about 40 and about 300 AU, 500 AU or so, those all seem to be roughly in a plane. And that is one of the earliest pieces of evidence we had for a Kuiper belt, a reservoir of icy bodies that are out beyond the orbit of Neptune, producing some of the comets that we have. But there's a problem. The gravity of the sun, 2 light years away, or 1 light year away, or whatever the Oort cloud stretches out to be, is not all that great. Those things are tooling around at very, very slow speeds, almost not bound to the sun. They are bound to the sun, but not much. The problem is there are other stars in our Milky Way galaxy. And those other stars occasionally pass by the sun. And in fact, calculations show that these 3 stars, I love this one, Schlotz, pass within 51,000 AU. The Gliese 710, about 1.29 million years ago, passed within 10,000 AU, which is well within the Oort cloud. If you do like dynamic calculations to try to figure out what would happen to the Oort cloud if that were the case, it turns out that those stars would suck off a bunch of the comets, would actually pull them out into space. They would be lost into space. And over time, the number of stars in the Milky Way galaxy, it would seem that the Oort cloud would eventually erode away. So there's a problem. How is it that the Oort cloud still exists? Well, sometime in the 1980s, it was observed that there are a not insignificant number of comets that come from a region that is out beyond the Kuiper belt. It goes out to a few tens of thousands of AU from the sun, but seem to be in the plane of the solar system, roughly, kind of like the Kuiper belt. And if you do the calculations, if a star were to pass through this plane, it would actually disturb the motion of these comets, churn them up, and throw them into wild orbits in a roughly spherical shape in all directions around the sun. This is now known as the Hills cloud, which I bet most people have not heard of. The Hills cloud is thought to be a very dense region of bodies that are orbiting in roughly circular orbits that get disturbed every once in a while and kind of replenish the Oort cloud, keeping it going, so to speak. Now, when this disturbance happens, the bodies in the Oort cloud are not orbiting out in long, lazy circles. They're orbiting, they get jostled into long orbits with high eccentricity for the most part. And so the Oort cloud consists of a lot of bodies that come in pretty close to the solar system and way, way far out around the solar system. So the Hills cloud is a supposed region of space that is filled with a plane of comets that replenish the Oort cloud.
Hey, Brad,
Yes.
is there a distribution of the direction of the paths, counterclockwise and clockwise?
Yeah, they're mostly within the same direction as the planets, but the speed of the objects way out in the outer portion of the Hills cloud is low enough that a disturbance from a star going by, it doesn't take much to change the speed of that body. I mean, you're changing it by 1,000 miles an hour or 100 miles an hour in one direction or the other, and that would actually that could change its orbit. These things are so loosely bound that it doesn't take a lot of disturbance to actually knock them way out of whack. And so the Oort cloud is more random, but the Hills cloud is thought to be roughly in the plane of the solar system. So let's take a look at a few recent comets and just explore what their eccentricities are and that kind of thing. Sorry, I need to do this little thing about comet nomenclature here. So when you see a comet, you often see this strange code here that they give for modern comets, C2020 F3 Neowise. You guys remember Neowise, this was the pandemic comet. And if the picture's not credited, by the way, I took it, so this is my picture of Neowise. It's an easy comet to photograph, though, because it was really bright. So let's take a look let's break this down and talk about the components to the nomenclature of a comet. So modern comet names typically start with C, or P, or I, to represent whether or not it's just a comet that they discovered. P is one that has got an orbit that is recognizably periodic. It's going to come back around again within a human lifetime. It's a short period comet that we are going to be able to see time and time again. The year of discovery is always included. The month of discovery is always included, and it's included in a very strange way. They break the months down into the alphabet. So A is the first half of January, B is the second half of January, C is the first half of February, D is the second half, E, F, G, H, and they skip I. They skip I because it would be confusing because it looks like a 1. They skip it, and they go straight on to J. This is how they name they give you the letter. 3 simply means it was the third one that was discovered within that time frame. So that's January, February, March. This is the third comet discovered in the first half of March of 2020. Okay, and then very often you get the discoverer there. The discoverer in recent times tends to be things like Neowise. Neowise has discovered a lot. There's more than one Neowise comet. Neowise is a solar satellite, or an infrared satellite, the WISE satellite, that was originally designed to look for infrared sources outside the solar system, clouds of gas and dust between the stars. But once it ran out of its coolant, they redirected it to looking for warm, dim bodies coming into the inner solar system. It's still functional. They just rechristened it Neowise, and this is a comet that was discovered by that particular system. You also get Atlas. Atlas is a system of 5 different observatories spread around the globe that scan the skies looking for comets. You also get Swift, which is Pan-STARRS, which is another survey system. And then Swift is a comet, a system that is on the SOHO spacecraft that stares at the sun. Every once in a while a comet will come into view around the sun, and they happen to be particularly bright. Sometimes we don't spot them until they're very, very close to the sun, and then those comets are given the name Swift. There's a number of different systems. But if you yourself discover a comet and you happen to beat one of these systems to the punch, you can get your name on a comet. It is the only celestial body that can be named after you if you discover it. So get out there looking and try to beat the Vera Rubin Observatory in Chile, which is going to discover a heck of a lot of them. So we're going to get a lot of C2027 Rubin or something like that. Or I don't know if they've decided to make it the Large Synoptic Survey Telescope or something like that. So anyway, these are the prefixes. I stands for interstellar comet. And they do something a little curious for I. They don't put the year because it's presumed right now that I is not very common. So they go I and then the number. So the third interstellar comet, I3. Borisov was I2. And Oumuamua was I1. And that's how they do it. So there's a couple of other little ones that you kind of see fairly rarely. X means the orbit is not calculated. Typically that means there was like 1 or 2 observations and then it died and they weren't able to get a third one. Or it fell into the sun. It was spotted by the SOHO spacecraft and then slammed into the sun. Or it's an ancient comet that we didn't get enough good observations and so the orbit is not really that well known. And then finally, D stands for defunct comet. So if a comet kind of just couldn't emit gas anymore, it's considered defunct, or they just lost track of it. So that's also a D comet, and they can't figure it out. So these are all the prefixes that you will see in comet nomenclature, sometimes in the news when you get a comet. So here's a couple of other ones. So we've got 73P, so that is the 73rd periodic comet. The reason why they're not using the date in this is because this predates the use of the year. It used to be that you didn't discover comets very often, and so that you could just use a number for that. And so retroactively, these have been assigned periodic comet numbers. Halley is 1P Halley. They just gave the first periodic comet that we know of is Halley, it's 1P. And then a defunct comet, one particular example of a defunct comet is it's slamming into another planet, a planet. Comet Shoemaker-Levy was D, defunct, 1993 F2. So also discovered in the first half of March. So Shoemaker-Levy, as you guys know, this is when I joined the club, by the way, was to see Comet Shoemaker-Levy 9 through Wilkie-Circus telescope. And yeah, it was defunct now because it is no more. So let's take a look at a few comets. One comet that is often in the sky is Comet NK. It's 2P NK. It was one of the earliest ones discovered, so it gets a low number there. Its eccentricity is not super great, and it only goes out a little bit past Mars into the asteroid belt and has an orbital period of about 3 years. So that's a fairly common comet. It never gets super bright. It's usually like 10th magnitude or something like that. This is Comet Halley, 1P Halley. It has a very high eccentricity. It goes all the way out until, past the orbit of Neptune. Its semi-major axis is 17 AU, so that's almost out, that's half of the orbit, but you remember, that's only half of the orbit. So if you take twice that, the sun is going to be way, way off at one side, and with an eccentricity that's really high, this is going to go out past Neptune a little bit, and its orbital period is 70 years. The reason why it's 70 years and not 200-ish years like Neptune is because its orbit is extremely long and thin, so it spends a lot of its time swinging around the inner solar system, picking up a lot of speed here. My picture of Comet Hale-Bopp. This is a little star cluster here, M34 in the background. This was taken on film. Comet Hale-Bopp has a very high eccentricity, but you'll notice that its semi-major axis is only a little less than 200 AU. But its orbital period is around 2,500 years. So we're getting out really, really far. So this is one of those maybe inner hill, outer Kuiper belt kind of comets. We didn't get to see this one quite at its best, but it was definitely visible here. Comet McNaught back in 2007. If you took a trip down to Australia, this picture was taken in Australia. It was like the comet of the century so far. This comet got up to a magnitude of like -7, brighter than Venus. I mean, really, really bright. This would have been probably what you would have seen with your naked eye had you been observing it. It was pretty spectacular. I was able to see it kind of in the sunset really well from here in Ohio. There was a period of time where it was bright enough to see kind of like Venus in the sky, but we couldn't see the tail very well. There was a period of time for a few weeks where some very faint outer wisps of the tail reached up in our region. You could see them poking up above the horizon in Ohio. Its eccentricity is kind of strange. Coming in, it had an eccentricity just a bit higher than 1, which means that it was screaming into the inner solar system. All things considered, nothing, with no perturbations, it would have screamed right back out of the solar system to wander between the stars. It would have been an interstellar comet. But it got nudged some million years ago or so, just enough to fall into the inner solar system. And then once in the inner solar system, either a combination of the jets or interactions with the bodies of the solar system reduced its eccentricity just a tiny bit so that it's now captured by the sun. The sun didn't give it up quite so soon. So it was thought that it came in from around 33,000 AU. We're talking more than a light year. And it's going to go out to the inner hills region, about 2,000 AU, a couple 10,000, 20,000 year orbit, something like that. So this is an interesting case where the orbit actually changed. Now this happens a lot with these comets because when the eccentricity is really, really close to 1, a tiny little nudge can send it over the edge one way or the other. Here's another one. Oh, yeah, I thought I had a second example of that. But no, yeah, so I had one that I forgot to include that sent it the other way, that actually is now escaping into the cosmos. This one never had a chance. This is Comet 3I Atlas. And this one was discovered earlier this year, and its eccentricity is 6. Which means that the sun is not going to have much of an impact on its motion. It's going to bend the motion a little bit, but it's not stopping nowhere, no how. It's going to fly in and right back out. Now it does have a couple of little nudges to the eccentricity. The eccentricity has changed a bit from the jetting of the comet, which is making everybody go, ooh, it's not gravitational. But it's not nearly enough to bring it to a stop because it's going much, much too fast. Its eccentricity is way, way high. So it doesn't have an orbit. It's just flying in through space, not captured by the sun, but nudged a little bit by the sun's gravity, and is now going to fly back out into the cosmos. So that is the eccentricity. So finally, we get to the modern era. We know where comets are. We know, how to calculate their orbits. We know how, where the bodies are placed. I will stop if you want to. Section. Okay. What is a comet? So this is distinct somewhat from the why is there a comet. So not everybody attempted to explain comets as portents of doom. Some people actually tried to figure out what they physically are. And one of those people was Aristotle. And Aristotle had a weird conception of the universe. He had this model of the universe where down on the ground, everything was corrupt and awful. Earth was a messy, muddy place, plague and wars and everything like that. The sky up above was pristine and wonderful. The Earth was actually made of fire, water, air. Earth, fire, air, water. Yes, okay, there we go, 4. And the universe was made of a fifth substance, the quintessence, the fifth essence of the universe, and it was pure. Anything that was below, according to Aristotle, below the orbit of the moon was part of the realm of Earth and made of those normal earth, air, fire, water substances. And he thought, given the misbehaving of the comets, that they must be of the Earth. They're not acting like the planets and the stars. The stars stay fixed, the planets move in very predictable patterns. And so he basically thought that the Earth had emanations, earth farts, basically. And those went up into the sky and became ignited. So Aristotle's idea was that they were in the upper atmosphere. Now there's an easy way to figure out whether or not that's the case. The easy way to figure out whether or not it's the case is to see where the comet is in the sky from Athens, and then also see where it is from Alexandria. And if it's up in the sky, it's going to move appreciably between the two. Now, people didn't really have the wherewithal to do that and coordinate their observations. And so nobody really made the nobody really made the leap to say, hey, you know, parallax shows that this thing is not close to us. But this particular philosophy of the way comets were lasted a very long time, until probably just prior to Kepler, because people weren't really sure what comets were. It helped that they didn't behave like planets on the ecliptic. Sometimes, oh, another thing, sometimes there was more than one at a time, so that, you know, emanations from the Earth might ignite in 2 different places. And the other thing that was really important is that they vanished. They actually disappeared. You know, planets stick around. These things, emanation burns up, disappears. That's why a comet goes away. And if you've ever seen a comet, you guys have probably mostly seen comets. We've had a good run of them lately. They seem to be little wispy clouds of something. That's a reasonable explanation as to what a comet might be. So Aristotle, in the 4th century BC, came up with these plans. Here's his idea. I will read. When, therefore, material gathers in the lower region, the comet is an independent phenomenon, but the exhalation, he calls it, is formed by the movement of one of the stars, either by the planets or the fixed stars, then one of them becomes a comet. So he thinks that this exhalation goes up, looks like a star, but then turns into a comet at some point. So this is his book, Meteorologica. Meteor is the Greek word for weather. And so comets were considered to be aspects of the weather. The word meteor comes from the same root. Meteors were considered to be parts of the weather. In fact, for a long time, people thought comets and meteors were the same thing. One was just moving a lot faster. So he thinks they are more developed than shooting stars. And they moved from place to place because of the movement of the upper atmosphere. It took until around 1531 for the people to actually observe comets in a systematic way. This guy, Petrus Appianus, people tended to give themselves Latin names. He was Polish. Observed that comets' tails tend to point away from the sun. Nobody had ever taken note of that. Remember that 4th century drawing I showed you? But Petrus Appianus noted that, and he said, yeah, maybe it has something to do with the sun. You know, maybe these things are more related to the sun. So this gave people the idea that perhaps they aren't of our atmosphere. You know, because if they're pointing always at the sun, that's not what's going to happen when emanations ignite in the sky. This was only the Europeans, however, the Chinese, of course, beat us to it here in the West. They made the same observation. This was only discovered in retrospect by about the 11th century. So several hundred years before that, Chinese astrologers and astronomers discovered that comets pointed at the sun regularly. So the age of the telescope came along, and we actually got a better appreciation of comets, because for the first time, we could actually see them up close, make them a little bit brighter in our vision, and study them intently. And so let's take a look at the very simple anatomy of a comet. We'll go through this quickly because you guys probably know it fairly well. There are, generally speaking, two main tails of a comet. You've got the dust tail. That's pretty self-explanatory. As a comet comes into the inner solar system, dust sloughs off. It gets kicked out by the jets of material and orbits around the sun independently of the comet itself. Depending on how big those pieces of dust are, they will either follow the orbit very closely, or they will be swept behind the comet a bit more when the pieces of dust are a little bit lighter. This tends to follow roughly the orbit of the comet. It fans out a bit. Different from that is the ion tail, which is actually made up of charged particles coming off the comet. These get illuminated by ultraviolet light from the sun. They get ionized, and the solar wind actually pushes them directly away from the sun. So the solar wind is going out in all directions. And so if you want to know what direction the sun is, you actually follow the ion tail directly to the sun. Now occasionally, you'll get something called an anti-tail. Now this could be one of two things. Let's take a look here. Here's a picture of Comet Hale-Bopp that I took down in Conquest Hollow, by the way. Orbital path is roughly this line. This goes roughly to the sun. So if we go close up on Comet Tsuchinshin Atlas here, we can see very, very nicely the anti-tail that this one had. The anti-tail are heavier pieces of the comet that are right in the plane of the comet's orbit, and they tend to follow, they tend to be a little bit behind the comet, a little bit in the orbit. They actually drift very, very slowly away. But perspective gives us the ability to see this anti-tail. Now, the problem here, let me show you. The problem here is that there aren't many objects in this region. The dust and the particles are very, very thin. However, it sweeps out a very, very large area in space. And so we tend to see the anti-tail when the comet is roughly in the plane of Earth's orbit and we are seeing it edge on. If the comet is above or below the plane of Earth's orbit and is going perpendicularly to us, we tend not to see the anti-tail very well because we're seeing it not through the thickest part, we're seeing it through the thinnest part, and it's spread out more. So, so you can get, like from here, this point of view, this material is spreading out along the orbit, so the comet is kind of going like this around the sun, and this material that is drifting out from behind the comet there is seen.
Hi gang, this is Brad. The recording stopped at this point because the battery died, so I thought I would continue the talk on my home computer here. Obviously, I do tend to talk long and the battery only has so much power, so I will continue here for the last few minutes of the talk on my computer. So I was talking about the anti-tail. Let's move on a little bit to humans' understanding of what comets are in fact made out of. Our earliest evidence for what comets were in fact made up of came from Giovanni Battista Donati, who in 1858 actually looked at this comet, C1858L1, which we now call Comet Donati, the Great Comet of 1851, and actually performed a visual spectroscope analysis of the comet. Nowadays, when we do spectroscopy, we actually do it with photography, and the lines that are produced by the different elements in the visible spectrum are marked down on film. However, at that time, the technology of photography was not advanced enough to actually do this very well, so he looked through his telescope using a spectroscope or a prism that actually split the colors of the rainbow up into or split the light of the comet up into the various colors of the rainbow, and was able to determine that the comet was in fact made up of energized gas, or at least part of the comet, the ion tail, was in fact made up of energized gas. It helped that this particular comet was exceptionally bright. This was kind of the, the greatest comet of the middle part of the 19th century. And he got something, I mean, this is obviously a photograph, but he saw something like this. Some of the highlights here actually indicate that the comet is in fact made up of glowing gas. And one of the more dominant gases in this particular comet happened to be carbon-2. So 2 carbon atoms stuck together. But he saw a number of other different gases there. He saw methane, and a little bit of carbon or cyanogen gas, and carbon monoxide as well. So Donati actually confirmed that comets were in fact made out of the same stuff that we humans are experiencing here on the ground, and people were able to compare the visual impression of the spectra of a comet with laboratory tests here on the ground. This is a more modern spectrogram of a comet. This was Comet 2001 Q4 NEAT. The only reason I chose this one is because when I Googled spectra of a comet, this is the first one that came up, and it shows the various molecular components of the comet. You'll see that there's some ammonia. You'll see that there is hydrogen in the comet. We've got 3 different elements, 3 different spikes in the spectra which show hydrogen. This is hydrogen beta right here. This is hydrogen gamma. There's some carbon-3, cyanogen gas, of course, and then the OH, which is called hydroxyl. That is actually a component of water when it is ionized. One of the hydrogens actually flies free, and you get ionized hydrogen and the hydroxyl atom, which are the various components of water. So it shows that in fact there might actually be some water in the comet as well. You wouldn't get ionized water very often in this part of the spectra. You wouldn't actually see that very well. So it came to be clear that the comets were made out of some pretty common things. For example, water and the hydroxyl ions were there, or at least the hydroxyl and the hydrogen ions were indicative of the fact that water was present. The nitrogen was in fact seen, N2, which is most of our atmosphere is made up of nitrogen. The one of the more common gases that are emitted by a comet is carbon-2, which shows up as green. You've probably seen a large number of comet pictures where the coma of the comet is very green. That's usually carbon-2 or carbon monoxide, a little bit of the thing that would kill you if you left your car in the garage too long while you're sitting in it. That would not be a good thing. But carbon monoxide is also kind of green. It's a little more toward the blue end of the spectrum, but combined they produce a nice, lovely green color. Carbon-2 and carbon monoxide are both very common in comets. Also, carbon dioxide shows up fairly often, and sulfur dioxide. The smell of rotting eggs comes from sulfur dioxide. Cyanogen, as we saw in the in the episode with the comet pills, everybody was worried about the cyanogen gas. Fortunately, it's extremely tenuous. We will not be poisoned by the cyanogen gas from a comet, even if we pass directly through the tail. There's just a little bit. Although cyanogen in great enough quantities will kill you. Hydrogen cyanide also will kill you. There's very little hydrogen cyanide. It's extremely attenuated, but it does show up in comets. You get ammonia, and you get methane. Uranus and Neptune have a lot of ammonia and a lot of methane. There's a lot of ammonia in Saturn and Jupiter, for instance. So these are common comet constituents that are actually seen in the spectra. These are seen in the visual spectra. But what's interesting is comets have a lot of very light elements, and based on our models of how the solar system formed, the inner part of a newly forming stellar system tends to be extremely hot. There is a strong solar wind, and very light elements tend to get blown back from the star that is forming, the protostar that is forming. So in an inner solar system, when it is actually forming, you don't get a lot of water or carbon dioxide or hydrogen. These elements are swept away by the force of the newborn star. So you get an interesting situation in our solar system. The inner planets, Mercury, Venus, Earth, and Mars here, turn out to be mostly heavier elements that can withstand the blast of sunlight that pushes the lighter things out into the outer solar system. And then you get the gas giants and the ice giants, Jupiter, Saturn, and the ice giants, Uranus and Neptune, out in the outer portions of the solar system. They're made up of primarily lighter elements. Well, comets have a kind of a mixture of some gas and dust. So you get a little bit of both. Now, Earth was in a very hot, violent part of the solar system. Actually, the Earth's moon was formed out of a gigantic titanic collision, which would have caused all of the water on the surface, were it to have had it, to have been blown away. The gigantic collision that formed the moon would have blasted the water and the light elements out into space from the simple heat of that collision. Plus the solar wind would have done that. So why does Earth have water? Well, for a very long time, it was expected that the early Earth was, after the moon formed, bombarded by comets. We know that comets have a lot of water in it. There's a lot of ice in them. So the things that make up our oceans and the nitrogen in our atmosphere were thought to have been deposited by comets. Actually, you get sort of replenishing the materials that were lost in the violent early ages of our solar system, and so Earth actually ends up with oceans as a result. And so this was for a very long time in the 20th century the model of how Earth got its oceans. There's a bit of a problem, however. If you take a look at the makeup of individual comets, and you can actually do this with both spectra and by satellites that pass through the tails of comets and collect the dust and the ice from these comets as they pass through the tails, and you figure out the deuterium to hydrogen ratio. Deuterium is simply hydrogen with a neutron in its nucleus, and deuterium is obviously a little bit heavier than plain old hydrogen, which is just one proton. And so deuterium tends to stick around a little bit in the inner solar system, tends to not get blown away quite so much as just plain old hydrogen. Hydrogen is blown away a little bit better. a little bit of fractionization. So different parts of the solar system actually end up having different amounts of deuterium in them. And if you model the amount of deuterium and hydrogen in the Earth, which is over here, and compare it to the different bodies in the solar system in which we know what the deuterium to hydrogen ratio is, you'll actually find that comets tend to have a little bit more deuterium than Earth's oceans. We actually have, the comets actually tend to have, strangely enough, they actually end up having quite a bit of deuterium in them. Whereas the asteroids between Mars and Jupiter's orbits tend to have about the same as Earth. So even though comets seem to have a lot of ice in them, it actually turns out that the rocks that make up the solar system, the asteroids in the solar system, also have water in their geologic components. There are rocks that have water in them as part of their crystal lattice. And so perhaps comets did deliver some water to Earth. However, it appears that asteroids probably did most of the heavy lifting in that regard. So the general consensus now is that most of the water came from the busy inner solar system and not the incredibly distant outer solar system. So that is an interesting model of what comets are in fact made of and what they are doing for us. However, there are some other constituents to comets. And in recent years, we've actually sent a spacecraft by various comet nuclei and have been able to determine the constituents of the tail of various comets and the dust that is coming off of it. And a lot of interesting materials have been found getting sloughed off of comets as they go around the sun. Things like methanol and ethanol. These are different alcohols. These are organic molecules in the sense that they have carbon in them. You get propanol, which is a constituent of propane gas, also butane, and you also get some of the heavier gases, argon, krypton, neon, xenon, and many, many more. Finally, one of the more interesting things that has been found lately is, let's skip that. These are some of the comet missions here that have gone by. You can actually see these are the different missions that have passed by comet nuclei in the past. Here's one, Stardust. This one actually collected some individual dust grains as it plowed through the tail of comet Wild 2. That's how you pronounce it, Wild. And they were returned to Earth. Interestingly enough, they were caught in this aerogel material, even though the individual particles were moving at many thousands of miles an hour relative to the spacecraft. This aerogel was actually able to slow them down very gently, and at the end of each one of these little trails was a tiny little speck of dust that scientists back home were able to analyze and figure out what was in the comet. Another comet that was visited recently was Comet 67P Churyumov-Gerasimenko. This was visited by the ESA's Rosetta mission, and I'm just going to show you. This is really cool. You can actually see the dust jets coming off of, or the gas jets coming off of the comet as it gets warmed up. This was kind of a contrast enhanced image. These jets were actually quite faint, and they were brought out by image processing. You can kind of see the place where they were sort of photoshopped. But this is the real jets over the comet. They were just enhanced in this image. However, not enhanced is this sequence of images. I'm gonna click on the go button, which actually shows you the general environment around the comet. Now, in the background, you'll see some stars moving by. They move kind of steady, but going every which way, these little lines here, most of those are little dust grains that are floating around the nucleus of the comet, and it gives you a really good sense of the kind of chaos of the inner part of this particular comet. And I love this video. It's just astonishing. Beautiful mile-high cliff there with the stars in the background and a whole bunch of different little specks going around. Occasional cosmic ray hits on the chip that's actually taking these photographs, but most of the dust that you see flying around is actually real honest-to-goodness dust. It's actually stuff that comes off of this comet. I just think this is one of the most cool videos I've ever seen. So from these, we actually were able to determine that, in fact, there are materials in comets that are the building blocks of life. And you can actually go to a supplement store, if you are a health fanatic or like to supplement because of your weightlifting hobby, you can actually go and buy a substance that was found in the body of a comet. Glycine was actually recently found in comet Wild 2 as it passed through, as the Stardust mission passed through that particular comet's tail. And so glycine is just one of many amino acids that were present in comets. And so while comets may not have brought the water that gives us life here on Earth, comets may have in fact brought us some of the raw materials out of which early life was perhaps made. And so comets have had an impact on us, and I find that pretty extraordinary. I think I'm going to stop here. I think you should probably go out and whenever you get a chance, look at a comet. I like this website. It's called Weekly Information About Bright Comets. If you just Google those exact words, you'll come up with this list. It gives you a list of the brightest comets in order, from brightest to dimmest, and about where they're expected to be in coming weeks. It will give you a map of the comet against the sky and the ephemeris of the comet, so you can plot it yourself. You can also pull these into astronomy software to plot them, which I did with Comet Wirjas, which is actually visible currently, and it is said to be visible, if it's a clear night, in binoculars. It's probably about magnitude 7.5 right now, and it's setting in the southwest. It's actually going to get higher and higher and higher. It will get dimmer over the coming months, but it'll actually get easier and easier to see because it's going to rise out of the sunset as time goes on. And this is probably the best one to actually go out and look at if you are interested in viewing a comet right now. There are obviously going to be ones in the future, so keep looking out for them. And I think I'm going to stop now. Thank you guys very much for making it this far. And I hope if you are interested in astronomy, you can make it to a meeting of the Columbus Astronomical Society at some point. I promise you, not all the talks are this long. I just have a reputation for going a little bit too long. But thank you for hanging out with me. Thank you.